Happy morning, dear friends. Here's yours, Dr. Ajanta. Welcome to Demystify with Ajay. Dear friends, in our previous session, we discussed about model assessment using various metrics, which helps us to decide which models to keep and which one to discard. And today's session, we are going to discuss some more techniques for training better models. Yes, that are overfitting, underfitting, bias-variance trade-off. These are foundational concepts in machine learning. And they are very important because they explain the state of model based on their performance. The best way to understand these terms is to see them as a trade-off between the bias and variance of the model. Okay, let's understand one by one about which we are just going to talk about. This first one is overfitting. Dear friend, overfitting occurs when a statistical model or machine learning algorithm captures the noise of the data. Intentionally, overfitting occurs when the model or this algorithm that fits the data too well. And to be the point, this specifically occurs if the model or algorithm shows a low bias. But high variance. Kindly just observe it. Okay. And overfitting often a result of an exclusively complicated model, and it can be prevented by fitting multiple models by using validation, or you can just say cross validation. Okay, so this one we are just going to discuss in our next session. Okay, actually this validation or cross validation, it is to compare their predictive accuracy on test data. Okay, we are just going to discuss it. And dear friends, this overfitting, a model set to overfit the data when it generates a hypothesis that accounts for every example. Okay, when a model trains on too many features, okay, we are just going to see first of all, let it have too many features. Okay, so if it has too many features, the hypothesis become extremely complicated. Consider a case in which you have one column feature and you need to generate a hypothesis. So this would be a simple linear equation. Let I just write it here. So this would be our equation, and here this equation is for a hypothesis for a line. Okay. Now consider a case in which you have two columns and in which you cross the columns by multiplying them also. So the hypothesis become as like y is equal to, and of course kindly just observe how many weights you have. So here it is only two features. This is x1 and x2 are the features, and when this become towards a product of the both, here we have one more. Okay, so here, and of course added to the bias. Dear friends, while the first equation here which we yield a line, and here this second equation is yield to a curve, because it is now a quadratic equation. You can also specify, rather than specifying, you can just say it is a quadratic equation. But the same two features could become even more complicated depending on how you engineer your features. Okay, here furthermore I just specify. So this is weight 1, weight 2 here, and feature 2. And here I'm just going to make the product of this, and not for, kindly just observe further, 1 the whole square and weight 5 x2 whole cube plus b, and the same set of feature has now given rise to cubic equation. So this equation will have the proper, or we can just say, yeah, this have a property of having a large number of weights. Where this would be used? Of course, if a simple linear equation have one weight and one bias, of course, this is what. And yeah, the quadratic equation has three weights. Kindly just observe, three weights and one bias. And the cubic equation has 5 weights and 1 bias. And of course, dear friend, one solution here for overfitting as a result of too many feature is to eliminate certain feature. And this exact eliminating this certain features, yeah, this exact technique is called lasso regression. And yeah, I just let you know, this is also, we are just going to discuss it under hyperparameter, and after this cross validation, this exact lasso would be included. Now, if we are having too long, kindly observe, too long training. Dear friends, the model starts training by initializing the vector of weight such that all values are equal to 0. So during training, the weights are updated according to the gradient update rule. And this systematically adds or subtract a small value to each weight. So as training progress, the magnitude of the weight increases. Kindly just observe. For this too long, if the training goes on for a long period, okay, the magnitude would of the weight would increases. If the model trains for too long, the model weights also become too large. It just goes on keeping. So the solution here for overfitting as a result of large weight is to reduce the magnitude. So this is what here we have to reduce the magnitude and magnitude of the weight to as close to 0 as possible. And of course here this exact technique of reducing the magnitude of the weight towards 0, it is specified as like ridge regression. Of course, this also we are just going to see it in detail in coming 4 sessions. Now, let us just come towards the underfitting. Dear friends, this underfitting occurs when a statistical method or machine learning algorithm cannot capture underlying trends of the data. And initiatively, underfitting occurs when the model or algorithm does not fit the data well enough. So specifically, whenever we just say underfitting, yeah, if the model or an algorithm shows low variance and high bias. Underfitting is often a result of an exclusive simple model. And here, as I have already specified, this both overfitting and this underfitting, yes, lead to poor prediction on new data set. And here, consider an alternative situation where we have just seen in previous one, overfitting. See, in which a data has a 10 future. Okay, if we have a 10 future, but you only make use of one future, and if you are creating a model hypothesis, and if you are having it in the sense as like this, and making an equation for a hypothesis for a line. However, that is an equation for a straight line, but your model is probably ignoring a lot of information. The model is oversimplified and is said to underfit the data. So the solution to underfit is to provide the model with more future, or conversely less data to train on, but more future is better approach. Here I am just specifying 2 important things, that is this variance and bias here under underfitting, and towards the variance and bias towards the overfitting. Okay, now what is the bias and variance? Let I just give you a detailed discussion about this. Okay, bias is different between the average prediction of a model and the correct value which we are trying to predict. A simple And a model with high bias pays very little attention to the training data and oversimplifies the model. If I just want to specify it in a simple line, yes, errors from training data. That's his bias. And when specifying this and variance is a variability of model prediction for a given data point or a value that tells us the spread of our data. And dear friends, a model with high variance pays a lot of attention to training data and does not generalize all the data which has not seen before. And here to be specified in a simple definition, yes, errors from test data. Yes, so well, to understand the concept more clear and better, let me just make it for create a concept divided into this bias and variance for regression and classification. Let me just see one by one. Okay, so first of all, let me consider a regression model. Okay, under this regression model, let I just make you a simple functionality. So here I am creating a model and let it just has its data point towards the actual and to the prediction like this. And kindly just observe here this degree of polynomial, here it is 1. And when on just observing this, let I just name it as model 1. And here, let me just go for model 2. Here, of course, we have the data points like this, and towards the prediction, let me just make like this. Actual and towards the prediction. And let I just go for the model 3rd. And let we have like this. Actual and towards the data points. And here, yeah, degree of polynomial, let I just have here as 2 and degree of polynomial here as 4. Now kindly just observe one thing, dear friends. We can see clearly that model 1 comes under underfitting. That is, bias is high. Okay, bias is high and variance is also high. And when coming towards the model 2, and kindly one more thing I just want to specify. Yes, this model 1 has not captured the trends properly, or the model is too simple, maybe like this. And hence it's obvious that the training and testing accuracy will be hampered. And as I have already specified, yes, bias is a error resulted from the training data, while variance is error resulted from the testing data. And here the model 1 will have less train and test accuracy, that is, will have high bias and high variance, which comes under underfitting. And I just go towards this model 3, jumping towards here. Similarly, in model 3, the model has trained too good. Kindly just observe, it is too good on training data. The reason it fails for testing is low test accuracy. Since the training accuracy for this model 3 is high and test accuracy is low, model 3 will have bias low and high variance. So this come under overfitting. Now consider model 2, as the model 2 isn't just right exactly. It is the one right model where the model has trained well on training as well as the test set specifically. Okay, so here the reason model has high training accuracy, that is low bias and low variance too. So now let's consider this the same thing for a classification. Okay, so I just go with the classification. Rather making it in a thing, let I have a diagram, let I just go with the tabular column. So we have, this is the model 1, and let me just take training error, that is bias. Okay, here it is 2%. So what, and testing error, it is of 18%. And model 2, training error, it is 24%, and testing error, it is 28%. Coming towards model 3, training error, it is less than, less than 10%, and testing error also less than 10%. Now, when I just take it towards this, dear friends, as we can see here, our classification model 1 has low training error while having a high testing error. As explained the concept earlier, we can conclude that model is having low bias and high variance. That is, this model 1 is clearly overfitting. And similarly, we can conclude our classification model 2 as clearly, kindly just observe, as underfitting model. By using just even seeing this value, we can just say, yeah, coming towards this, here you can just specify as like 24% of this is error, that is high bias, and of course high variance. Okay, so it is not exactly recommended, and it is clearly it is specified as like underfitting model. Let me just go towards the model 3. Dear friends, this exact model, kindly observe, yes, it has low bias and low variance, and yes, of course, this is most generalized model and of course most recommended model to train on. So now we have discussed about, yes, underfitting, overfitting, bias and variance for regression and classification model. Okay, what's next? Here, we understand that overfitting can be detected by monitoring the model's performance on the training data versus the unseen, that is testing data. But what exactly this test data is? It is just random data that has not yet been seen by the model during the training phase. And yes, we are referring that unseen data as a test data. And here I just want to specify. Let's just imagine we have 100,000 sample data. So this is our sample. Okay. So yes, let me just have 1 lakh. Okay. So 1 lakh samples of data to begin with. Okay. So you can take out a portion of data. So let's say 10% of it become our test data. So as if this become test data, now this 1 lakh, from this 1 lakh samples, we have only 90,000 training data, and here 10,000 test data. So hope you understand this. Okay. Now, however, it is better to not just split over original data into train and test data, but also in a validation set. See, especially when we want to perform hyperparameter tuning on our model, let's say that our maybe out of 1 lakh original samples, we held out 10% of it to become a validation set, and another 10% become the test set. So therefore, here this 90,000, yes, exactly how it becomes, it is equivalent towards the validation. So here this become 80,000 as a sample for training data, 10,000 for validation, and remaining 10,000 for test set. Okay. So you might be wondering, why do we need a validation set apart from this test set? Actually, we do not need it if we do not want to perform hyperparameter tuning or any other model centric approaches. This is because the purpose of having a validation set is to have an unbiased evaluation of the test set using the final version of a trained model. A validation set can help us unbiased evaluation of a test data set because we only incorporate the validation set during the hyperparameter tuning phase. Once we finish the hyperparameter tuning phase and get the final model configuration, we can then evaluate our model on the purely unseen data. That is what we just call as test data. And here I just want to specify one important note. That is, if you are going to perform any data pre-processing, that is any data pre-processing as like missing value imputation or future engineering, standardization, label encoding, more the things are there. You have to build the function based on the training data set. Yes. And then apply it to the validation and test data. Do not perform those data pre-processing set on a full original data before data splitting, because it might lead to data leakage. Kindly just observe this. And here, dear friends, there is no specific role when it comes to choose this proportion for each of the training, validation and test set. So you have to choose the split proportion by yourself based on the condition you are faced with. However, the common splitting portion used by data scientist community is most probably as like 70-30 or 80-20. And to the least as like 90-10. So for the training set and validation and test set respectively. And usually the validation and the test set will have a proportion of 1:1. So in such a case, if I just specify this, okay, 80 and 20, if it is a set, yeah, my splitting proportion, how it just comes, 8 for training, 1 for validation and 1 proportion for test data respectively. Now that we are aware of train, validation and test set concept. Now let we just make use of that in our splitting process. Let me just see it in practical. Okay. So yes, dear friends, we are just going to discuss the same thing under practical thing. And of course, this exact example, for this example, of course, I have used this car data, which we have already discussed. Okay, so by even though you can just get it done from UZI machine learning repository. Okay, so now let I just include that important necessary libraries, and of course I have included this train test split from sklearn model selection to split the data into 2 parts. Now before reading the file into your notebook, kindly just see here, we are having the car data. Okay, and this exact car data, it is from UZML repository. I have already specified, and we have already discussed about the parameters of what this data it has. Okay, and of course, dear friends, this exact data, when you just make use of each and every functionality, okay, as like yeah, even I can just specify this is exactly for buying, the purchase price of the car, and this maintenance or cost of the car, and here number of doors on the car, how many persons, that is carrying capacity of the vehicle, and about the size of the luggage boot, and here estimated safety of the car, and of course whether the car it is accepted or not that comes under the target data. Okay, so now we have this. Okay, now kindly just observe, dear friend, this info. I just scroll a little to have you a view. Okay, so in order to get information about the column in the data as well as number of records, yeah, we used info method. Okay, and kindly just have a note of this range index. Range index value just shows here this, that is number of records, which is 1728. Now what's next? You need to split the data that is contained in this data frame DF, okay, into training data set and evaluated data set. Okay, so yes, let me just split into training and evaluation. And here, dear friends, we have specified training size as 0.8. You can directly specify as like evaluation or test data, and here we specifically mentioned that a training size is equal to 0.8, so which is 80% of the data is assigned to training data frame. And yes, random state ensure that your experiment are reproducible. Without random state, the data is split differently every time using a different random state. Okay, so with random state, the data is split the same way every time. And of course, we are just going to discuss what is the random state here further. So first of all, let I just make it random state is equal to 0. Okay, and let I execute. Now, once after splitting, let me just check only the training data frame. Observe here, dear friends. And here, specifically towards this training DF, I have executed this info. And you should have observed the column name, okay, and matches that's the same here in our data frame. But observe only 80%, and here the index, int index, that is 1382 entries out of 1728. Now let I just go for the evaluation data frame, which we have 20% now. So that one. So yes, of course, dear friends, kindly just see here. This will give you the same column name and the record numbers, and of course you just able to see how to know the exact values. And yes, dear friends, the remaining data, 20% of data, that is here in our evaluation. So now what is next? Of course, you are just going to evaluate it by making the model and goes further. Okay, now coming to an important point. Now you know how to split your data. Whenever you split your data, the records are going to be exactly the same. You could repeat the same process and number of times and notice the range of entries in this evaluation. The implication of this is that you can't repeat your experiment. If you run the same exact snippet or code, you will get different result every time. Also, if you share your code with your colleagues, or they will get different results. This is because the compiler makes use of random number. This random number are not actually random, but makes use of something called pseudo random number generator. The generator has a predetermined set of random number that it uses as a result. You can specify a random state that will cause it to use a particular set of random number. Now I just want to show you, yes, exactly, dear friends, kindly have a view. So the key to reproducing the same result is called random state. You simply specify a number, and whenever the number is used, the same result will produce. This works because the computer don't have an actual random number generator. Instead, they have a pseudo random number generator. This means that you can generate the same sequence of a random number if you set a random state. Okay, consider here, let I just show you in this exact figure. See, the column or your random state. Okay, here we have, this is the column or the random state. And if you pick 0 as the random state, the following number would be generated. That is 41, 52, 38, 56. These are the number. However, if you pick 1 as your random state, a different set of number will be generated, and so on. So, dear friends, this exact, previously we have specified random state is equal to 0. Yes, that example I have specified. Yeah, previously, let I just have. So here, random state is 0. So that the experimental was repeatable. If you just specify some other random state, yeah, let me just make over here. Okay, so here let we have, so same thing, training size 0, 1, random state 1 I have specified. Let we have the data. And for your information, first of all, let we view this training data and have a view. So kindly just observe, you print the first 5 records, okay, and kindly observe what are all the exact top 5 rows from the training set, training evaluation set. And if you just go on towards this evaluation, okay, kindly just observe what is the exact record here. So the exact output should be the same thing, okay. Here, whatever you specify in the exact records, I just scroll above, dear friends. Okay, if in such a case, if you want to have, I just include this and make a df. And here, let we have the head and see what we have, 1085 and see 1659. Okay, so the similar thing we are able to see. So the goal of this session, yes, is to get reproducible split. If you run the code, you will get the same records in both training data and evaluation data. So you may proceed to run that code a few times on every system and verify that you can get the same records in both the data set. Whenever you change random state, yeah, you will get a different set of training and validation. But how do you find the best data split to train your model? When you don't have a lot of data, the recommended approach is to make use of all your data. But how do you retain validation data? If you make use of all your data, yes, the answer is to split the data into number of parts. And this approach, yes, of course, we are going to see that in our cross validation. Yes, dear friends. So yes, this exact approach is called cross validation, and we will be looking it in our next session. And furthermore, we are going to discuss about this lasso regression and ridge regressions also. Okay, so yes, dear friends, if you found this video helpful, don't forget to hit the like button, subscribe to the channel and turn on notifications so you don't miss any of my upcoming content. So drop a comment below if you have any questions or suggestion for future topic. And always from my side, keep learning and stay curious. Yeah, see you in the next video, dear friends. Happy learning.